Part 3. Learning how to count. Part 2. We left our last talk with a discussion about a linear algebra of primorial minors of differing depth. Let S be a sequence of gaps of length r in some Sm, with the current prime greater or equal than r, and let P sub m0 be the smallest such prime. Furthermore, let Tm sub sk be the set of k counts of the substrings type from m greater than m0 plus k. The following is true by construction. For every such sequence, there exists a set of k greater than or equals to r constants c sub s, which equals the numbers, such that the counter tem is the linear sum of the constants times the deeper primorial minors. We construct c sub s as follows. For all m greater than or equal to some m0, let om of m and k be a k by k matrix, whose members are om of I and j equals the ith plus 1 primorial minor at index m plus j for all I and j in the appropriate range. T of m0 and k at s be the counts of s, r string from m0 to m0 plus k. To find Rc sub s, the set of indexes for each minor primorial, we solve the following linear equation. A count array equals our putative index array times a primorial minor matrix, Om. That is, our putative array of constants is the inverse of Om, our primorial minor matrix, times our count arrays. Also, for each string S, there is the smallest k equals k0, where C sub S sub j equals 0, for all j greater than some k0. For example, the count of twins only needs the second minor primorial. Having S3 in hand allows us to count gaps of 8 and 10. Our gap set allows us to begin counting them. Gaps of 8 are generated by substrings of 2, 4, 2, and all its spawn, while gaps of 10 are generated by substrings of 4, 2, 4, and all its spawn. These require m0 greater than or equals 3, or p greater than or equals 5, since they need the fourth minor primorial defined. To solve this, we will need data from 3 iterations, or from S3 to S5, or to 11 primorial, also known as Z sub 2310. Having 11 minus 1 primorial equals 480 members. We'll just give the results. That is, we have exact results for every possibility of gap strings that sum to 8 for every S-model iteration bigger than or equal to 3 or primes bigger than 3. Notice the string 2, 4, 2 is atomic, while the pairs 2, 6, and 6, 2 can bubble from coalescence. The same treatment for everything 10 gives us an interesting surprise. The string 4, 2, 4 is atomic and boosted above background by 2, because it occurs twice in S3. This leads to the fact individual gaps of 10 occur more frequently than gaps of 8. Also note, gaps of 10, as they must, has coalescence terms. The algebraic sequence, for every gap larger than cousins, must have a complement of coalescence terms. This is because cousin gaps were the last individual gap types to coalesce into existence, with their progenitor subsets dying at their birth. And this is how all atoms are created. We'll stop here because the set sizes and characteristics are exploding exponentially. We suggest the serious reader write their own software to probe deeper. S11 or Z sub 31 primorial is easily accessible by any modern laptop. Even a tablet with 32 GB can probe this. By the way, the first minor primorial, for p equals 31, has 30,656,102,400 members. A closing observation about out-of-order first occurrence gaps. Every possible even number will eventually be sampled as a gap in some iteration of the model. This is because of the complete level of sampling of the CKM. There are 2 possible orders here, index order within an iteration, and between iterations. That is, it can happen that for some G sub A less than G sub B, with both first occurrences occurring within the same iteration, and G sub B having a lower index than G sub A. For example, in S4, gaps of 10 occurred before gaps of 8. But it can also happen that G sub B occurs in SM, while the first occurrence of G sub A is in the next S iteration. We see this with gaps of size 20. S6 equals Z sub 13 primorial has gaps of 18 and 22, with gaps of 20 conspicuously absent. Gaps of 20, however, appear first in S7. Though a painstaking exercise, we encourage the serious reader to examine these sets and see for themselves the underlying mechanics. In our next video, we discuss gap pair rules and develop what we call short-range rules. We show the gap distribution, for all its internal patterns, has vast classes of band gap constellations beyond the pairing of twins or cousins. For more information, please see the next lectures, or Google multiplication modulo n along the primorials with its differences and variations applied to the study of the distributions of prime number gaps.